Hi friends, continuing our discussion on priority queues. Now let us see how this heap helps in implementing a priority queue. So first let me define what a heap is. So heap basically is a tree. Tree means will consist of nodes, and basically there are two types of nodes. One parent node, and then there is a child node. So that's how a tree would look like. So this is a parent, that's two children of this, and this is the parent of these two children, and that's a parent of these two children, and so on. So it's something like family structure. We have a parent, children. That's a first thing. Next thing is it's a binary tree. That means we'll have maximum two children, not more than two children. So each node can have maximum of two children. So that's property of a tree. So what a heap is, heap is a special type of tree that is almost complete. That's the first thing. That means layer wise the nodes are added. So if you just want to give a number, then this can be 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. That's one thing. And if you see the order in which the numbering are done, then the left child is defined first. So for a node 0, its left child is called 1, right child is called 2. For node 1, its left child is 3, right child is 4. For 2, left is 5, right is 6, or in other words, the child numbering is done from left to right, that too layer wise. So we have 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's how it is. So this is the way the nodes are being added. So that makes a heap. So if there are only say 4 or 5 nodes, then this will be node 0, 1, 2, that makes node 3, node 4. So 1, 2, 3, 4, 5 nodes are there. Now if there are 5 nodes, then this cannot be placed like this. 3 and 4 cannot be placed like this, because the left child has to come first. So they are ordered in this fashion: 1, 8, 9, 10, 11, 12, 13, 14, 15. So this cannot be 8. 8 has to be here only. So the positions of these nodes are fixed. So as you keep adding or removing nodes, yeah, the structure gets updated. But only thing is, so when a new node is added, then we are sure that this will be the new node that's getting added. And if you want to delete any node, then of course this is the node which has to be deleted, because in this list this is the last entry. So when you delete, the last one has to be deleted, because all other way the tree should be complete in this layer wise fashion. So you can't just delete node 2 without deleting 3 and 4. So if node 2 has to be deleted, 3 and 4 also have to be deleted, or node 2 is deleted, then one of the two have to go up here, and so on. So that's a heap action. The question comes is, how does this help in solving our priority? So let's talk of priority. Say that's our minimum finding problem. So each time you are trying to find a minimum, then what we require is called a minimum heap. So the properties of minimum heap is simple. The value of parent must be always less than or equal to value. You can't have equal to, because each value is supposed to be unique, of the children. So if you are talking about values, say if we have data like 1, 3, 6, 8, 10, yeah, there are 4 nodes. So the structure is supposed to be this 3, and the fourth one has to be here. Now what you have to say is the parent has to be having a value less than the children. Therefore, whatever values you write here, say, let me number them. So index 0, 1, 2, and 3. So the node 0 should have a minimum value compared to node 1, node 2. Node 1 should have a minimum value compared to node 3. So node 0 should have a smaller value, node 1, node 2. So that's or node 0 happens to be on the root, therefore it has to have smallest value. So the value node 1 will have will be 1. Right. Then what else? What can be node 1 and 2? So node 1 can be 3, and node 2 can be 8, and node 6 can be here at third position. So any problem? Yeah, it appears that 6 could have come here. Yeah, you can have 6 here, you can have 8 here. The only condition is to satisfy this. So only condition is to satisfy this, that is the parent should have value smaller than the values of the children. That's the property of a min heap. So in this, what would happen is, when you look for minimum entry, then it is always found on the root. So whenever you want to see what is minimum value in this list, just look at the root, and the root says what? Yeah, definitely 1 is smallest among all these, so that's the easiest way. So it's a order of 1. So constant time action, you can say, to identify the minimum. Now if you add a new number which you call insert, so what do you want to insert? Say if you want to insert 10, so where should it go? Of course it should go here, which is the index 4. That's a property of the heap. If you want to add a new node, it has to be at this position only. You can't add any other way. It has to be at location 4 only. It can't be any other place. Now can I write a 10 here? 10 here. Yeah, 10 is greater than 3. So 10 can be child of 3, no issue. So that's not a problem. So what next? Can I insert another value? Say 5. Of course, where should I insert them? Then the only option I have is insert here, whose index is 5. That's a property of heap. So you can't forget that the next number should be inserted here. So what number you are trying to insert? You are trying to insert 8. Is it possible? Definitely no. Then what to do? The one option is exchange these two values. So you can get 5 moving upward, 8 coming downward. So will this be min heap? Okay, let me check it. So node 1, its parent is 0, value is 1, node 1's value 3. So moving to lower level, the value should increase. So this was 1 at level 0. It is 3 at level 1, no issue. It is 1 at level 0. It is 5 at level 2, no issue. 3 at 1, 6 at 3, no issue. 3 at 1, 10 at 4, no issue. 2 at 5 at 2, and 8 at 5, no issue. So after making this correction, yeah, this also is okay. So this is okay, this is okay, this is okay. So all seem to be okay. And if you look at it, we are talking about a set which is having so I can write a set any way I like. So in this, what is minimum value? Minimum value is 1. So where can I find it? Just look at the root. At root, what is there? Minimum value is 1. So that's a property of heap. Simple thing is layer wise, you just look at it. The parent should have smaller value compared to the child. If that one condition is satisfied, then yes, it's a heap. And please don't get confused with a binary search tree. Nothing to do with the left side, right side and all. This has nothing to do with the left side, right side. So if you try to insert one more number, what can I say? Maybe 7. Okay, where is the place for 7? So the next place is this, whose index is 6. So can we insert 7 into that? Let me try. I add 7 here. So 7 is greater than 5. Yes, this min heap condition is satisfied. Therefore, this is still a minimum heap. So that's now left value is smaller, right value is bigger, left value smaller, right bigger. But when it comes here, left is bigger, right is smaller. So nothing. Left, right, we don't have any issues. We have issues only with the parent and child. That's a heap. So heap differentiates between the levels, whereas a binary search tree is works with the left and right subtrees. So here we are not worried about left, right. We are only worried about levels. So at any level, a given node is at its right position as long as its children are greater than itself. So with this, what happens is all the time the smallest element is always at the root. So that's the advantage of this. Smallest element is always at the root. So if you want to find what is smallest element in the list, just look at the root. So that gives you a constant time checking. So that makes the fastest action possible for searching the minimum value in the given list. So that's what we call a heap. A brief introduction about a heap. In this case, we have taken example of min heap. Let's see in detail how the heap actions are taken, and when a node is inserted, what happens, when a node is deleted, what happens. All these issues we need to look at. So these are the issues we look in our coming sessions. So keep watching. Thank you.